All right, everybody, welcome back. This is Ripley. Now we get to start having fun. Now, some of you may have, when we first saw our little chart, remember our chart? I don't know why I'm drawing it. I can jump on the internet and make it even more fun. Boom. Remember this? Some of you may have seen this Z and had your spidey sense start tingling a little bit. You may have said, wait a sec, Ripley, I've seen Z's before. I know that there was a formula, Z equals x minus mu over sigma. Remember what that did? That reduced any sample, if it was normally distributed, it told us how many standard deviations a specific value, a specific data value was away from the mean. Guess what? This Z-score is also the Rosetta Stone that I was talking about. This converts any normal curve to the standard normal curve. And that is so important. Standard normal distribution. That is so important. And it's actually, it's so simple and so elegant. I mean, just look at it. All right, let's do a couple of problems just to play with. All right, this isn't a very long section, but it's so beefy and the ramifications of it are just amazing. Okay, excuse me. How's this sound? I would like to draw a person at random. All right, I don't know how I'm going to do it, but I'm going to randomize it. I'm going to pull Social Security numbers. I'm going to do whatever I can to try and randomize it. And I'm going to grab a person at random, and I'm going to try and figure out the probability that their IQ is larger than 120. All right, I've got it equal to. Let's go greater than or equal to. Now remember before I said it didn't matter if this was greater than or equal to, less than or less than or equal to. All right, so let's think about this for just a second. Grab a person, test their IQ, find the probability that their IQ is greater than 120. Well, let's remember a couple of things. First and foremost, IQ is a normally distributed variable. Sometimes you'll see it written this way. Normally distributed variable with a mean of 100 and a standard deviation of 15. All right? Now, I don't happen to have an IQ chart. The only chart that I have is this bad boy right here, this guy that we have, all right? The standard normal curve. However, I am not stymied at all. Watch how this works. This is really cool. I'm simply going to rewrite this probability statement. Okay, I'm going to write it as, because this is this Rosetta Stone thing. I'll stop saying Rosetta Stone. That just sounds overly dramatic. This is exactly the same as saying, what is the probability that a Z-score is greater than or equal to some number? All right, and this formula right here tells me what that number is going to be. So watch how this works. I'm going to stumble over here. All right, I know that the Z value, the number of standard deviations away from the mean that a person with an IQ of 120 is going to be 120 minus 100 divided by 15. All right, so this is going to be, last I checked, 20/15, right? Or what do we got? 4/3? 4/3, or approximately equal to 1.33. Now, what does that tell us? We just converted this into this. That is so cool. All right? So really what we're asking is, instead of the probability that x is greater than or equal to 120, what we're asking is, what is the probability that z is greater than or equal to 1.33? And the only reason, I can't say this strongly and vehemently enough, the only reason we're allowed to do this is because we know that IQ is a normally distributed variable. If we didn't know that about IQ, we would be in trouble, okay? All right, well, let's figure this thing out. I'm going to pause. I'm going to take a deep breath. I'm going to let you guys play on the table. So I'll get us to the table, and I'm going to see if you can try and figure out the probability that Z is greater than or equal to 1.33 using the table. All right? Here's me taking my deep breaths. Hit pause on your browser, and then we'll do it together. Okay, you ready? Hopefully you paused, gave it a shot. Again, especially when you're getting your brain wrapped around this, draw yourself a curve. Ooh, that's a bad curve, bad curve. Okay, I know that this is 0. I'm saying this is z equals 1.33, and I'm looking for this area. Okay, drawing that curve is so immensely helpful. I hope, I beg that you do this. Okay, so here we go. Oh, good God, Ripley, what am I going to do? This chart only gives, I'm going to reduce this, it's in my way. This chart only gives me areas to the left of the z-score. All right, well, let's look. First I'm going to find a z-score of 1.33 using my chart. So here's 1.3, right? And if I stumble all the way over to here, I get 1.33. So this value, 0.9082, is the probability that a person is below 1.33 standard deviations to the mean. Look, that's how the table works. Well, look at this. Through the magic of technology, I know that what that implies, because our chart gives us those areas, what that implies, now I lost it, what was it, 0.9082? Because my chart gives me, I'm going to make this guy big, tells me that this area right here is 0.9082. Well, I know this is a probability distribution. So I know that the area under the curve has to equal, say it with me, 1. So this probability that we're talking about right here is just 1 minus 0.9082, right? Which is simply 0.0918. So the probability that you select a person at random and have their IQ test at or above 120 is 0.0918. Isn't that cool? All right, let's do the same thing. Let's do it with heights this time. I'm going to change this sucker back to black. All right, I want to find the probability that, let's see, I'm 6'1", and I've got friends that are 6'2", and I got some friends that are 5'10". Okay, so I'm going to select a person, a male, excuse me, at random, and I'm going to find the probability that that male is between, let's see, what did I say? I'm 6 foot, so that's 6'1", 60, what is that, 73, 74. Let's go, is between 75 inches, which is 6'3", and let's go 5'9", which is, what is that? 69. Okay. Now, we know that men's height is a normally distributed variable with a mean of 70 and a standard deviation of 4.5. We don't actually know that because I just made it up. How could you possibly know that? Okay? So here's what we're going to do. I'm going to draw the curve, and then I'm going to let you guys play for a sec. I'll give you a little break and let you play on it and see if you can figure it out. So draw your curve. First things first. My curves are looking a little respectable. I'm not going to lie to you. Now, excuse me. I'm actually going to draw this curve, and then watch what happens. This is going to be the height curve. And then I'm going to do the whole thing in blue. And when I'm done, I'm going to change it into the standard normal curve. Okay? Remember the standard normal curve. I'm eventually going to change it into this guy right here. This is my standard normal curve. All right? So I know 69 lives. Whoops. Try that again. I know that, I love the eraser feature on this bad boy. I know that 70 lives here. So 69 is going to be about here. I'm just guessing, to be honest. And let's just say, I don't know, 75. 75 lives there. So I'm finding that area right there, which represents this probability. Okay? However, I don't have a men's height table. I can't emphasize that enough. I don't have a men's height table. So what I'm going to do is I'm going to use my Rosetta Stone. Sorry, it's that beautiful. It actually glows through the computer. And I'm going to turn these values into these values. All right, so all I do is I go z equals 69 minus 70 divided by 4.5, which is what? Negative 1 4.5, right? Which is what? Negative 2/9, affectionately known as negative 0.22. I think that's right. And then z equals 75 minus 70. Oh, I'm getting fancy now. Over 4.5, which is what? 4.5, which is 10/9, affectionately known as 1.11. Okay? Oh, by the way, that reminds me, when you're finding z-scores, always round out to hundredths. Why, young Ripley, should we, I'm not really that young, but why should we round to hundredths? Because that's how our charts work. Notice, this is 1.20, 1.21, 1.22. So the vast majority of all charts, if you're using a chart, I'm going to show you how to use your calculator to come up with those areas as well, which are far more specific and far more accurate, more precise, but oftentimes it's just easier to jump on a chart and do it. Okay? Now, you ready? You're going to try this. I'm looking for the probability that instead that a randomly chosen individual is between 69 and 75, excuse me, randomly chosen male, adult male, is between 69 and 75 inches tall, and I've turned it into the probability that Z is actually between negative 0.22 and positive 1.11. Okay? Now, take a deep breath. I will pause for a moment. Try it on your own and see what happens. By the way, before you do that, notice that this curve, which used to be the curve representing men's heights, because of the using of the Z formula, we turned it into this guy. So now 70 is actually 0, 75 is 1.11, and 69 is negative 0.22. Okay? All right, enjoy, and we'll jump on this and do it together here in just a second. Okay? All right. Okay, you ready? So, let's go over to our chart. Let's see, I need to find some negatives. This part of the chart doesn't have any negatives. Let's go over here. So, what did I say? Negative 0.22. So, let's see, that's 0.02 right here. So, I'm going to follow this column down until I get to negative 0.2. So, this value right here, by the way, this is exactly the same chart as is in your book. I'm hoping that you're using that in your book. This tells me that, excuse me, gotta wet my whistle, that the value to the left of the z-score of negative 0.22 is 0.4129. Now that value represents area or probability. So let's go label our little drawing. Let's label that. Okay, so that sucker right there tells me that this in here is going to be 0.4129. This blackened area right there. Okay? Now let's go find 1.11. All right? 1.11. Let's see, 1.11. Hopefully, again, you're looking in your book. I got 0.8665. Now, I'm a little punchy today, so bear with me. You can probably tell. 0.8665. So I go back here. Now, this is going to be a little nastier, so I'm going to change the color. I'm going to have to change my notation a little bit here, because otherwise this is just going to be a nightmare. That tells me that the area from 1.11 to the left is 0.8665. The problem is I want this area in here. How am I going to be able to figure out this area in here? Well, it's easy. If the area from negative infinity to 1.11 is 0.865, and the area from negative infinity to negative 0.22 is 0.4129, what do? Well, you guessed it. I just subtract them. Just subtract areas. It's just a simple geometric concept, right? So 0.8665, and I'm going to subtract 0.4129. What do I get? 6535, is that right? 4. So 0.45, and that's my answer. Look at that. If, now granted, I made this normally distributed variable up, but if that's true, the probability of finding somebody who is between, what I say, 5'9" and 6'3" is that one randomly selected individual is 0.4536, or approximately 45% of the time. Yeah, so cool. So much fun. Okay? All right. One more thing, just for fun. All right? I would like to find, let's find the heights of of the following. We'll go with women this time. Of the following. Let's see. One. Let's go the 99th percentile for women. And 2, let's find the middle 88% for women. Okay? Now, whoops, for women. I don't know why I did that, but we'll do it anyway. Okay? Now, this presumes, what did I say? I said it before, that women's heights are normally distributed with a mean of, I think I said, what did I say, 65, and a standard deviation of 2.5. It was a smaller standard deviation, and I believe that's accurate. I think some people say it's 64, and others say it's 65. All right? Okay, so the 99th percentile for women. In other words, what is the height of a woman such that that height is taller than 99% of everybody? Now, this is going to take what we've been doing and flip it on its head. It's going to flip it around perfectly. All right, so for part 1, first things first. Hey, it's a normally distributed variable, right? So I know that there is a value. Remember, if I'm in the 99th percentile, I know that on this curve, remember, I'm talking about women's height right now. There is a value above 65 such that 99% or 0.99 of everybody is below some corresponding, we don't want to jump the gun here and go to Z yet. I gave away my tricks. There is some theta value, some height that is that is taller than 99% of all women. All right? Now, I don't have a chart for women's heights. Let's change colors. It'll be more fun. All I have is this silly little Z chart over here. However, remember, 99th percentile implies that 99% of everybody is in this area, is in this probability region, not the Z-score. These are Z-scores on the left column and the top row. But what I'm looking for is I'm actually looking for that Z-score. I'm going to turn this X value into a Z-score that tells me about the 99th percentile. Okay? All right, so let's stumble in here and see if we can find 0.99. 0.99, 0.99. Just keep swimming. You know what? I think that's about as close as we're going to need to get. All right, 0.9901 is close enough for government work, as they say. So what that tells me is, let's see, what is that? What's the Z-score? Get out of there. What that tells me is that I'm in my own way, aren't I? No, I'm not. Here we go. That there is a corresponding Z-score of 2.33, which tells me that 99% of everybody is below 2.33 standard deviations away from the mean. So let's go back here. I know that Z equals 2.33. Now you may say, well, Ripley, that's great. All right, I know now that 2 1/3 standard deviations away from the mean represents the 99th percentile. Great, but I haven't answered the question. I want the height of the woman. Well, guess what? We still just use the same formula. Z equals X minus mu over sigma. Well, Z is 2.33 minus, there's the X that I'm trying to solve for, right? That's what I'm looking at. X minus mu, which is 65 inches, divided by 2.5. Look at that. I have a simple Algebra 1 equation that I can solve, right? Just using algebra. If I multiply through by 2.5, and I, add 65, so 2.33 times 2.5, and then if I add, make sure I do this right, 65, that's what? 70. This is 70.825. So a woman who is approximately 5'11", closer to 5'11 than to 5'10", is going to be in the 99th percentile for heights. Isn't that cool? All right, let's try number 2. All right, let me change colors here real quick. I just love playing with these. They're so much fun. Number 2, draw yourself a curve. Ooh, that's a terrible curve. My bad. Getting a little lazy. All right, here we go. Women's heights still. So I know that 65 lives here. All right. Oh, by the way, just to be exhaustive here, this is actually z equals 0. That's why I changed this all to blue. All right. Once I use this z-score, this curve turns into a standard normal curve, which has a mean of 0 and a standard deviation of 1. Okay, so we're off to the races. Go turn back to black. Back in black. All right, now what am I looking for? I'm looking for the heights that correspond to the middle 88% of women. All right, so in other words, I want an x over here. This is actually going to be a negative x and a positive x over here. And in here, 88%, 0.88% of all people are going to live there. Okay? Now this one's going to get a little tricky, so let's really think this through before we get crazy. All right, my chart doesn't give me the middle 88. It only gives me values to the left. So let me see if I can explain this right. I'm going to change colors. Go to red this time. If this is the middle 88%, and I have this symmetric property of the standard normal curve or any normal curve, doesn't that tell me that to the left from negative x to 65 is going to be 0.44, as is to the right, so 0.44. Let me draw, that's kind of hard to see. Let me erase this here real quick. Sorry, guys. All right, that tells me that from this x value to the mean is 0.44. And from here to here is also 0.44, because when they add up to the middle 88. Now I also know that the distance from negative infinity to 0.65 is 0.5. True? Think that through. Make sure I'm not lying to you. Remember, the area under the whole curve is 1. It's symmetric. So the area from 65 down, excuse me, is going to be half of it, or 0.5. Which tells me that the area to the left of this x value right here is going to be 0.5 minus 0.44, which is affectionately known as 0.06. And now I have the way my chart works. Now, remember, when you do this on your computer, it's going to be a lot simpler to do nasty little bits like this. Okay? But there's also things that your computer can't do. All right, so what I'm going to do is I'm going to find the z-score that corresponds to these x values such that the value to the left of that is 0.06. So you ready? All right, this isn't anywhere near, so let's stumble back up here. 0.06. 0.0606. Oh God, it's going to be halfway in between these guys again. So let's call it negative 1.555. Ooh, that's awful. Negative 1.555. Okay, we'll go back here. Get real fancy. All right, now I'm going to need to get a little bit bigger because things are starting to get out of hand. So if I redraw this thing, I'm going to redraw it because that thing just got ugly. Now this time, because I'm talking about standard normal stuff, I'm going to slap a 0 here. I'm going to have a z-score over here of, what did I say? Negative 1.555. Remember, this guy right here is 0.06. Let's make sure, double check, because you guys know I do crazy things. 0.0, yeah, close enough, right? That's a terrible 1.5, yeah, sorry guys, it is what it is. Okay, now, remember, symmetric. We got this symmetric property, which means that if this is z equals negative 1.555, then this right here is z equals positive 1.555. And the area out here must also be 0.06, which implies that the area in between is, ta-da, it's got to be 0.88, which represents the middle 88% of women. Problem is we haven't answered anything yet. I need to know what that height is. Well, I've got z values. I know that it's a normally distributed variable with a known mean and a known standard deviation. So now I just need to apply my glorious, glorious, glorious formula. So I've got 1.5, oh, this is definitely going to take a calculator, isn't it? Is equal to x, which is the data value that's going to correspond to the z value or the z-score, minus what would we say, 65 divided by 2.5. And in a puff of algebra, notice I don't put an equals there, because then I would scream and yell at me, and that would sound weird. 5 times 2.5 plus, sorry, I'm cheating with my calculator, plus 65. And what am I going to get here? Whoa, what do I have? Oh, I put minus 65. What a ding-dong. Second entry, sorry guys, plus 65. And I get 68.89 inches. 68 point, what is that? 5'8"? All right, well, almost 5'9". Now, if I do negative 1.555 equals x minus 65 over 2.5, that's going to give me, remember what I did? I just found the x value that corresponded to that, I guess it would be, what, z sub 0.06, that's another way to think about it, or that corresponded to the right boundary of that. If this is x, I'm going to call that negative x, okay, even though it's not going to be negative when we're done. Excuse me. So we got to respect thy negative. Remember, had God been a mathematician, the 11th commandment would have been respect thy negative. So times 2.5 and plus 65, and I get x equals 61.11, 5'1". In other words, in summary, we could say 88% of all women are between, what do we say, approximately 5 foot 1 inch tall and 5 foot 9 inches tall. Now, I'm taking great liberties with my rounding here, but hopefully you understand. Is that not the coolest thing that you have done all day? If it isn't, you just must not be alive. All right, we're going to have lots more fun with this. Believe it or not, it is the foundation for everything. I hope you enjoyed. We're done with 6.3. So we'll see you tomorrow, and I'll teach you how to use calculators and all that good stuff. Have a good day.